So we have another type of temperature sensor, which is the resistance or resistance temperature detector. Okay, so the resistance temperature detector, it actually uses as a sensor materials whose resistance will change as the temperature of the material is changing. Okay, that is, if it is one that is having positive coefficient, the resistance of the material will be increasing as the temperature is increasing. If it's one that have negative coefficient, as the temperature of the process is increasing, okay, that is the process that is looking at, as it's increasing, the resistance, okay, of that element, the sensing element, the sensor, will be reducing. So here we have an example of it. So you see the resistive material, it is made up of a platinum, okay, platinum wire. So this platinum wire, once it is heated, the temperature will do what? It will change. So you see the range of temperature that you can use, it very wide range of temperature from -258, from the cryogenic region, to very high temperature of about 727 degrees Celsius or centigrade. Okay, so here, since the resistance is changing with a temperature, so how do we harness this variation to give us a representation of the temperature of the process that we are looking at? So you see that the RTD, or the resistor temperature detector, is connected to a Wheaton bridge. Are we seeing it? So at rest, that is at zero temperature, it is connected so that the deflection or the output from here will be zero. Okay, so as the temperature is changing from zero, of course, the balance of the Wheaton bridge will be altered because the resistance of the RTD will change. So let's assume that it's a positive coefficient RTD. As the heat is increasing, the resistance will go up. So as it's going up, the balance here will be altered, and then the output from here, the voltage that will be generated, that will come out from here, okay, from the Wheaton bridge, will be going up. Okay, so it is now fed into a meter that has been calibrated to give us a direct temperature reading of the process. So here is the RTD. Okay, we have the RTD, which is the sensing temperature sensor now, the sensing part. Okay, you can see it at the tip. Here we have the RTD. Then the connecting cable runs out, okay, into this junction box, which will be fed to your transmitter that will later amplify it and send it to wherever you want it to go. So as here is having contact with the process, as the temperature is changing, the resistance of the RTD embedded in it, okay, will be changing. Since it is connected to the RTD that could be here or in the transmitter, especially if it is coupled to your transmitter. So that RTD, the Wheaton bridge, I mean to say, not RTD. Okay, so the Wheaton bridge that is here, that imbalance that will be caused, we cause the generation of voltage, and that voltage will be sent to the transmitter for amplification, or sent to your local gauge or to the control room to give us the representation of the temperature, or a reading of the temperature in our process. So this is how it is connected in the feed. You see that the RTD is connected into the process. It has a direct contact with the process. Then the sensor wire, okay, is run to the junction box, and from the junction box it is connected to your transmitter or to your controller, okay, and there it could be amplified and sent to wherever it is sent to. So this is another form of sensor, the resistance temperature detector. So what you should put at the back of your mind now is that the RTD or resistance temperature detector uses a sensing element whose resistance changes with changing temperature. Are we getting it? So as the temperature is changing, the resistance is changing. So that resistance forms a section or a leg of the Wheaton bridge. Okay? That could alter the balance of the Wheaton bridge as the resistance is changing, and that can cause the generation of voltage. Okay? Whose magnitude is dependent on the magnitude of the temperature that is that the RTD is exposed to.